Hi everyone, I'm Michael, and I'll be talking about how to scale replicated state machine protocols with a technique we invented called compartmentalization. I'll begin by explaining what state machine replication protocols are. At a very high level, the goal of a state machine replication protocol is to keep multiple copies of some deterministic state machine in sync. This is just a fancy way of saying that we have multiple copies of some stateful service, like a key value store or a relational database, and we want to make sure that every replica of the data doesn't diverge. If we view a state machine replication protocol as a black box, it accomplishes this as follows. First, clients issue state machine commands to the replication protocol. In this slide, we have three clients issuing commands X, Y, and Z. If our state machine was a key value store, for example, then these commands would be sets and gets. Second, the state machine replication protocol totally orders these commands into a log. Finally, the state machine replicas execute these commands in log order. Because every state machine executes the exact same commands in the exact same order, every replica stays in sync. One of the most popular and widely used state machine replication protocols is MultiPaxos. A MultiPaxos deployment looks something like this. We have a number of clients, we have a number of servers called proposers, and we elect one of the proposers to be leader, which I draw with a crown. We have a number of servers called acceptors, and we have our state machine replicas. You'll notice that the leader and the replicas have copies of the totally ordered log of commands. MultiPaxos executes like this. To propose a command, X for example, a client sends X to the leader. The leader then sequences the commands into the log. It puts the first command it receives into the first log entry, the second command in the second log entry, and so on. Next, the leader performs a round trip of communication with the majority of the acceptors. I won't have time in this talk, unfortunately, to explain these messages in detail, but thankfully for the remainder of the talk, you won't need to understand the protocol that deeply. Understanding the flow of communication is all that's important for this talk. Finally, the leader notifies the replicas that the command X is chosen in log entry 0. The replicas place the command in their log and execute it. And finally, one of the replicas returns the result of executing the command back to the client. Here's the communication flow again for command Y. We go client to leader, leader to acceptors, acceptors back, leaders to the replicas, and one of the replicas back to the client. If you pick up a paper on state machine replication, more often than not, the paper will mention that MultiPaxos is slow. Specifically, that it has low throughput. Ideally, we could scale up MultiPaxos to increase its throughput, but it is widely believed that MultiPaxos does not scale. This is not actually true. I'll show you in just a moment how we can scale MultiPaxos, but first it helps to understand why people think that MultiPaxos doesn't scale. MultiPaxos has three main components, the proposers, the acceptors, and the replicas. Let's try to scale each component. First up, the proposers. Here I've drawn MultiPaxos with 5 proposers instead of 2. If we execute the protocol, we see that the performance isn't affected at all because the non-leader proposers don't do anything. In the normal case, the non-leader proposers are idle. Their only job is to take over as leader if the current leader fails. So, adding more proposers doesn't increase throughput. Next, let's try to scale the acceptors. Here, I've drawn MultiPaxos with 5 acceptors instead of 3. If we execute the protocol, we see that we're doing everything we were doing before and then some. Specifically, the leader is now contacting 3 acceptors instead of 2. This means that scaling up the acceptors actually makes the protocol slower. Finally, let's try to scale the replicas. Here, I've drawn 4 replicas instead of 2. Much like with the acceptors, increasing the number of replicas actually slows down the protocol because the leader now has to communicate with strictly more replicas than it had to before. In summary, naively scaling up the proposers, acceptors, or replicas either doesn't affect throughput or lowers throughput. Now let's see how we can scale up MultiPaxos in a slightly more clever way. To improve MultiPaxos' throughput, we first have to identify the throughput bottleneck. For MultiPaxos, that is the leader. The leader is the throughput bottleneck for 2 reasons. First, everything goes to the leader. Every command is sent to the leader, and the leader orchestrates all of the communication for the entire protocol. Second, the leader performs disproportionately more work per command than every other component. We can see that by counting the number of messages every node has to send and receive per state machine command, which I've drawn here as orange numbers in boxes. The replicas have to touch either 1 or 2 messages. The acceptors have to touch 0 or 2, but the leader has to touch 7. To eliminate the leader bottleneck, we note that the leader has two main responsibilities. The first is sequencing. The leader is responsible for totally ordering all of the commands. The second is communication. The leader is responsible for communicating with every other node in the protocol. Historically, these two responsibilities have both fallen on the leader, but this is not necessary. Our big idea is to first decouple these two responsibilities. We do so by introducing a new set of nodes called proxy leaders. Now, the protocol executes like this. A client sends a command X to the leader sequences the command as usual, but it no longer communicates with the acceptors or replicas. Instead, it sends a message to a randomly chosen proxy leader. This proxy leader then finishes executing the rest of the protocol by communicating with the acceptors and replicas. Sequencing is done by the leader, and communication is done by the proxy leaders. How does this eliminate the leader as a bottleneck? Well, if we look at the number of messages every component has to touch per command, we see that the leader has gone from sending and receiving 7 messages to now just sending and receiving 2. This eliminates, or at least alleviates, the leader as a throughput bottleneck. But note that the proxy leader now has to touch 7 messages. So have we really eliminated the bottleneck or just moved it into the proxy leaders? We have eliminated it. The reason is that the leader load balances requests across the proxy leaders. Every proxy leader is embarrassingly parallel, so we can scale up the number of proxy leaders until they are guaranteed to no longer be a bottleneck. In addition to decoupling, this is the second part of our big idea, scaling. Together, we call decoupling and scaling compartmentalization. I just showed you how to compartmentalize the leader, but compartmentalization is a generally applicable technique. Let me show you how to compartmentalize the acceptors and eliminate them as a throughput bottleneck as well. I said earlier that naively increasing the number of acceptors makes MultiPaxos slower. This is true, so we have to increase the number of acceptors in a more clever way. Specifically, we introduce multiple acceptor groups and partition the log across these groups. We're taking advantage of the fact that while every log entry needs a fixed set of acceptors, 2 different log entries can use completely separate groups of acceptors. In other words, we are decoupling the acceptors used across log entries. Now, the protocol executes like this. The top client sends a command X to the leader sequences the command in the first log entry and forwards it to a proxy leader. Because X is the first log entry, the proxy leader contacts the first acceptor group and executes the protocol as usual. Here, the command Y is placed in the second log entry, so the proxy leader contacts the second acceptor group. And finally, Z is in the third log entry, so the proxy leader contacts the third acceptor group. The fourth command would go back to the first acceptor group, and so on. Because acceptor groups are embarrassingly parallel, we can scale up the number of acceptor groups until they are guaranteed to no longer be the bottleneck. That's all I have time to discuss in this talk, but I encourage you all to check out the paper where we discuss how to compartmentalize replicas, how to compartmentalize batching, how to compartmentalize reads, and how to compartmentalize other state machine replication protocols in addition to MultiPaxos. Thank you so much.